Hello everybody, I'm back with yet another video related to the transverse shear stress. So you guys recall that I mentioned that for solid rectangle and solid circle, we could use those equations that we were talking about. So for example, for solid rectangle, tau max is 3/2 V over A, and for solid circle, tau max is equal to 4/3 V over A, right? But if you have a hollow rectangle or a hollow circle, then what do you do? So that's what I want to show you. So let me just erase this. I don't want to make this too messy here, guys. And I put this line back. Okay, here we go. So you guys recall that if you go back to the two videos before this, you'll see that I showed you how to find Q max for a solid rectangle. It became T times the depth h squared divided by 8. But what if I have a hollow rectangle? Well, just subtract the inner Q from the outer Q. So T outside, H outside squared minus T inside, H inside squared. Take the 1/8, factor 1/8 out. Okay. How about a hollow circle? So for a solid circle, we know maximum shear stress happens right at the center, right on the neutral axis. Q max, I showed you in the video, it's 2/3 C cube. For a hollow circle, guess what? It becomes 2/3 C outside cube minus C inside cube. So I have a very simple example here for you. This time I have a cantilever beam with two loads on it, 2,000 pound, 4 feet apart. The whole entire length of the beam is 8 feet, as you could see. So I want to find, and we have a hollow circle. So the cross section of this beam is hollow circle with an outside radius of 3 inches, inside radius of 2 inches. So I want to find what? Tau max, transverse shear stress due to shear load V. Okay, so what did I do here? I first find the reaction here, which happens to be 2,000 plus 2,000, that's 4,000. And that's all I need. That's all I need. And that's my maximum shear load. Here we go. So if you draw the shear diagram, which is not necessary, your maximum shear is 4,000 pounds. Then remember, you cannot use those equations for solid rectangle or solid circle. You have to go and use this equation, the shear formula, tau equal VQ over IT. So if we use this formula, I went and I calculated Q max based on this equation. Here we go. It became 12.67. Then I calculated I here. I, remember, for a circle, kind of like half of J, but in terms of radius would be pi over 4C outside to power 4 minus C inside. So I calculated that for you, roughly about 51, a little bit more than 51 actually. So I just rounded it to 51. And then what is T in this equation, in the equation, or as it relates to our problem? Remember, T is where the shear stress is acting. Where does the shear stress acting? Here and here, right? So that would be what? The 2 thickness. Thickness times 2. What is the thickness? Thickness is C outside minus C inside. But you have to double it, so be careful. So that becomes 3 minus 2 is 1. 2 times 1 is 2 inches. So plug in the number. I just left the units here, so you see that the unit actually, you see how you have inch to the power 5 in the denominator and inch cube here, so you get inches squared. So you end up getting pound per inch squared in terms of the unit. And that's PSI. So 497 PSI. So I just wanted to make sure that you're aware of the fact that the for if you have a hollow rectangle, you cannot use the 3/2 V over A equation, or if you have a hollow circle, you cannot use the 4/3 V over A. So be careful with that. So you have to use what? The shear formula. By the way, the good news is that actually shear stress, this type of shear stress, transverse shear stress, is not important in design, guys. And what really causes the failure, or really controls the design, is Usually the shear stress due to twisting, if you have the twisting, the TC over J, or the bending stress, MC over I. So we'll see later on in another example that you see that actually what controls the design is, really the bending and the normal stresses that are developed as a result, the MC over I. And in some cases, TC over J. And we'll see that actually in chapter 8. So thank you for watching. Another video coming to you shortly. Thanks.